to this session of Global Poisson. Today, it's our great pleasure to have Pavel Etingof from MIT, and he will be speaking on short star products for filtered quantizations. So, Pavel, I'll give you the floor.
Okay, thank you very much. It's my first talk in Zoom, so if something fails, don't blame me too much. One good result of COVID-19 is that seminars became much larger. So I'm happy to speak here. And I thank the organizers for inviting me. So I will speak about short star products for filtered quantization. And this is my joint work with Douglas Stryker, who is actually an MIT undergraduate student who did a research project with me. And this is published in the paper on the archive 1909-13588. So let me start with reminder on Poisson algebras. So I will consider A, which is a commutative algebra over complex numbers with non-negative grading. So this means that I have a decomposition. A is a direct sum of A sub D, where D is non-negative. In degree 0, we have just the field C, and all the homogeneous parts are finite dimensional. And the multiplication preserves the grading. And I want to have a Poisson bracket on this algebra. So it will be a Poisson bracket of degree -2. So this means that the Poisson bracket maps A sub n cross A sub m to A sub n plus m minus 2. So in fact, this theory works for any Poisson bracket of negative degree, but and the most important cases are -1 and -2. This is sufficient for most applications. And -1 is contained in -2 because you can simply, if you have degree -1, then you can simply multiply all the degrees by 2. And here is a basic example, which is well known, of course. If you take the polynomial algebra or the symmetric algebra of a symplectic vector space V, and Poisson bracket then is defined by a Poisson by vector. It's a constant Poisson bracket with constant coefficients. So it's defined by a vector in wedge 2 of V. And the bracket of f and g is just df tensor dg evaluated at pi. For example, if you have the two-dimensional space, then we have just polynomials in two variables, x and y, where x is coordinate and y is momentum. And then we have a Poisson bracket of f and g is df over dy times dg over dx minus df over dx times dg over dy. Now I want to consider quantizations of such algebras, and one of the ways to consider quantizations is star product quantization. So this is a very old idea going back to basically Hermann Weyl, and then there is a big theory starting from a paper of 5 authors, Bayan, Flateau, Fronsdal, Lichnerovich, and Sternheimer in the 70s. And I'm going to consider star products which are equivariant with respect to the Z mod 2 action. So we have a Z mod 2 action which is given by -1 to the degree, and invariant. So everything I consider will be equivariant with respect to that action. So I will not say that always. So a star product on A quantizing this Poisson bracket is an associative product on the same space A, such that if you have elements of degrees n and m, then the star product of them is the summation over k of some bilinear expression ck of AB, where ck goes from an cross am to an plus m minus 2k. So it has degree minus 2k. So it's a bilinear map. So the 0th one is just the ordinary product. And the first one, its skew symmetrization is the Poisson bracket, which is this quantization condition. And then there are some lower order terms. So now I should say that normally in the discussion of star products, there is a Planck constant. But in this case, the Planck constant equals 1. So normally what you do is you write h bar to the power 2k times, or h bar to the power k times ck. But here, because we have a filtration, it's a particular kind of deformation where you can rescale the deformation parameter. And for this reason, we can set h bar to 1. That's what is done here. And so this is very classical. But now I'm going to give a definition that is recent and which was introduced by physicists Beem-Peelaers-Rastelli in 2016 in connection with their work on the three-dimensional superconformal field theory. So the point here is, see that a summation here, you can sum over all values of k, but actually the sum will only be up to the floor of n plus m over 2, because if you go above that, then this will land into A with a negative subscript, which is 0 by definition. However, a star product is called short if you actually the sum is shorter than expected. Namely, these ck of AB are 0 already when k is bigger than the minimum of n and m, which is obviously less in general than this n plus m over 2. So in other words, there is no terms in this star product in A sub d where d is less than the absolute value of n minus m. In other words, for example, if you multiply two elements of not of the same degree, two homogeneous elements not of the same degree, then you can never get a constant term. You always get constant term 0. So this is the definition. So any questions so far? So to ask a question, you have to press the bar and unmute yourself. Okay. So now I want to define the notion of a non-degenerate star product also. So we have this inner product. Suppose we have a star product, so then we can define this inner product on A, which is given by the formula inner product of A and B is the constant term of the star product of A and B. So a constant term is just taking the term of degree 0. And I want to mention that if the star product is short, then this form is 0 if the degrees are different, as I just mentioned. And therefore, the decomposition of A into degrees is orthogonal. So that's a kind of meaning of this shortness condition in particular. And the definition is that a short star product is non-degenerate if the corresponding inner product is non-degenerate in each degree I, which is equivalent to saying that it's non-degenerate on the whole space because the different degrees are orthogonal to each other. If you have questions, just ask them as I speak. Now, there is another approach to quantization, which is more common in algebra, and this is the notion of filtered quantization. So when you don't build quantization on the same space, but rather you take a different space, which is a non-commutative algebra, and it's associated graded, is the original algebra. So suppose you have a commutative graded algebra. So far, I don't fix a Poisson bracket on it. And I consider a filtered associative algebra bold A, which is not a direct sum anymore. It's just a union, nested union of pieces, which are called F sub D of A. So these are filtration pieces, and F0 is just the field, but then they get bigger as D grows. And the associated graded algebra is identified with this ordinary A. So associated graded of bold A is just the direct sum of FdA over Fd minus 1A, and we have these isomorphisms here, compatibly with multiplication. So filtered algebra means that Fi times Fj is maps into Fi plus j. And the graded then gets an algebra structure, and it should be just the same as the previous algebra A. And so I'm going to assume that I have a quantization which is again equivariant with respect to Z mod 2. As I said, everything in this talk will be equivariant. So this means that you have a automorphism S, which is involutive, and its associated graded is just -1 to the degree, as I mentioned in the classical case. So that's another approach to quantization, to build such a filtered algebra. And so then how is this related to the Poisson bracket? Well, so you have commutator of Fna with Fma because of the invariance condition. So it has to, well, it sits in degree n plus n m minus 1, but because of the invariance, actually it's n plus m minus 2. And so we have the leading coefficient map when we pick out the leading part of exactly that degree, and that maps an cross am to n plus m minus 2 for the old algebra A, which is not bold-faced, which is commutative. And this is a Poisson bracket of degree -2. And it's easy to check that this is a Poisson bracket. And so we obtain a Z mod 2 equivariant filtered quantization of this algebra.
Pavel, sorry, what's the meaning of this filtration preserving condition? Why is it a natural condition? What's good about it?
Oh, you mean the filtration preserving automorphism?
Yeah, that's right. That's if I understand correctly, that's the way how you get to degree -2 n plus m minus 2 instead of n plus m minus 1. But kind of what's this? What should we think about this automorphism?
Well, in examples like in the Mayal-Weil quantization, for example, which I will talk about in a second, you have a map which maps x to -x and p to -p for momentum p, and that's an automorphism of the algebra. So somehow this kind of automorphism exists in many applications. And again, if it doesn't exist, then you can simply multiply the degrees by 2, and you will just have the identity automorphism. So there won't be any condition.
Okay.
Yeah, I mean, it could be larger than 2, so you could have an automorphism of higher order like that, but there are not that many applications of that, and the convenient setting for this theory is degree -2. Okay, so now the question is the following: so how to relate those two kinds of quantizations? So if you have a star product, then you can define quantization just by taking the corresponding classical algebra and defining a new product on it. But can you go back? Well, go back, you don't need additional information because star product contains clearly a lot more information. So, and this is done using the notion of quantization map, which is also a very old notion going back to Weil. So, quantization map is a Z mod 2 equivariant isomorphism of vector spaces phi from commutative A to the non-commutative A, such that phi, so it preserves filtration, so it maps part D into part less than or equal to D, and associated graded of phi should be the identity, where associated graded of phi is just the direct sum of its action on each degree. So it's only a linear map. It's not required to have any properties other than being a linear map and these properties. So this basically means that it's a splitting of the filtration on this bold A. And in general, of course, it cannot be an algebra homomorphism because the algebra is commutative, but the quantum algebra is not. And in physics literature, you can often find this notation by phi of A. This phi of A is denoted by A hat. So it's a quantization of the classical observable A. And again, it cannot preserve the product, and it cannot even preserve the bracket, which is a more subtle statement and is called the Van Hove theorem, which means that classical symmetries get deformed when you pass to quantum mechanics, but also very well known. And so if you are given such a quantization map, then you can construct a star product. And in a very simple way, you just write that star product of classical observables A star B is you do the following. You quantize A, you quantize B using your quantization map. You take their product in the quantum algebra, and then you take you unquantize that and get a classical observable, which is this A star B. And then conversely, given a star product, as I said already, we can just construct a filtered quantization in a very simple way. You just take the same vector space, you take a new multiplication, which is given by the star product, and filtration induced by the grading, and the quantization map in that case is just the identity. And the lemma, which is very easy to prove, that this is a bijection. So this defines a pair of mutually inverse bijections between, on one hand, star products on A, and on the other hand, Z-mod 2 equivariant quantizations of A equipped with a quantization map. So in both sides, you're Z2 equivariant, actually. Okay, any questions up to this point?
So when you say that you are setting capital A to be by definition A with the star product, you mean that you are saying that's a algebra homomorphism. So the quantization, you are defining the quantization of A as the structure of A with the star product.
Yes, yes, yes. So in this case, I define it on the same space. Take the same space, but I change the multiplication so it becomes non-commutative, and that will be my algebra. Other questions? Okay, so let's consider an example now. So I have so let's consider the simplest example. I take the symplectic plane with Poisson bracket defined by this equation, yx equal 1. And in this case, we have a filtered quantization, which is well known, and which is the Weil algebra, or algebra differential operators in one variable. It has two generators, x capital and y capital, and the commutation relation, which is the Heisenberg relation, yx minus xy equals to 1. And this is a Z-mod 2 equivariant filtered quantization. And filtration is just given by the condition that the degrees of the generators are equal to 1. And we can also define a quantization map. There are, of course, many quantization maps. For example, so the quantization map means basically that for every monomial, you have to say how you are going to order it to get a differential operator. So we can put x's on the left of these or on the right of these, or we can do something intermediate. The most symmetric thing is this called Weil symmetric quantization, which basically says that if you want to quantize px plus qy to the n, where p and q are some numbers, this is p times capital X plus q times capital Y to the n. So that's a symmetrized quantization, which means that you basically take the average of all the orderings. And an example of that is if you quantize 1, you get 1. If you quantize x, you get x. If you quantize y, you get y. But if you quantize x times y, then you should get the average of all the orderings. So it's going to be xy plus yx over 2, which is, if you reorder this, this is going to be xy plus 1/2. And you can compute the star product that this thing gives under the bijection that I mentioned, and it turns out to be the well-known Mayal-Weil symmetric star product. which is the following. So you take two functions, a and b, two polynomials, and then you apply to it this bidifferential, infinite sum of bidifferential operators, exponential of dy dx minus dx dy over 2. So this means you write just the exponential power series and apply these powers to this thing. So this is an element of the tensor product of this algebra with itself. But then to get back into the algebra, you just multiply the components. So any questions? Okay, so for example, suppose I want to compute little x star, little y. So, so I'm supposed to quantize them. So I get capital X and capital Y. I multiply them in the quantum algebra. So I get capital X, capital Y plus 1/2. And then I have to unquantize, I get capital X, capital Y. But then phi inverse of capital X, capital Y is little x, little y times minus 1/2. So that's how we multiply them. And if we multiply them in the other order, y star x, we will get xy plus 1/2. And so lemma is that this star product is short and non-degenerate. So both of these are very easy to check. Shortness, for example, follows from the fact. So if you look at the formula here for the Weil-Mayal star product, if you have A of degree n and B of degree m, when you get to the smaller of the degrees and then go one step above that, then the derivative of that order is going to kill this polynomial and you will get 0. So this means that there are no terms here of degree where so this is a sum of powers of this thing divided by factorials, and the power is less than or equal than absolute value of m minus n. So is less than or equal than the minimum of mn, and that means that you cannot get below absolute value of m minus n.
Excuse me, Pasha. Morally, I do have a question.
Yes.
And the question is the following. So in this case, you obtained a short star product. And in my mind, this is due to the fact that essentially you started with some flat Poisson structure or Darboux.
Right.
But somehow here it almost appears as the choice of phi also enters in this. So I guess my question is, if I change phi, can I produce from a Darboux some sort of quantization which is not
yes,
short?
yes, absolutely. This is a great question which gets at the heart of what I'm going to talk about.
Oh,
and
okay.
Indeed, it's only short for this particular quantization map. Well, there are other quantization maps like left ordering or right ordering. For them, it also will be short, as you will see in the next slide. But of course, there are many quantization maps for which it won't be short. In fact, the main theorem will be that there are only finite dimensional space of quantization maps for which the star product is short, while the variety of all quantization maps is infinite dimensional. And another thing, another point that Marta made, which is also very good, is that this has to do with the fact that you're using constant coefficient Poisson bracket. For other Poisson brackets, we don't have such simple formula. And in fact, it's not easy to see why short quantizations exist at all. So in fact, the fact that they exist for many examples is a kind of miracle, which is one of the main points of this talk. Okay, so and you have a similar statement in several variables when you have a symplectic vector space, and the Mayal-Weil star product will have the form as here. You just take the Poisson bivector over 2 exponential, apply it to A tensor B, and then multiply. And in fact, this doesn't have to be symplectic. It could just be a Poisson bivector, which is degenerate. It also works in that case. And this star product is still short, and it's non-degenerate if pi is non-degenerate. It comes from a symplectic vector space. And more generally, we can, like I said, you don't have to be symmetric. You can use left ordering or right ordering or something intermediate. So we may consider a short star product for if you have a symmetric tensor eta in s squared of v, you can add it to pi and make a star product which is symmetric, which is not, so for example, this C1 is not going to be Poisson bracket, but will be Poisson bracket plus some symmetric tensor. And you can write it in this way. So you can relate. So if pi is non-degenerate, then eta is related to pi by some operator, which is a skew-symmetric operator from V to V. So it lies skew-symmetric with respect to the symplectic form. So it lies in the symplectic Lie algebra. And A star B is written in this form. And then lemma is that this star product is non-degenerate if and only if this operator is B plus 1 or B minus 1 is invertible. So if B doesn't have eigenvalue plus or minus 1. Obviously, since it's a symplectic, from symplectic Lie algebra, if it has eigenvalue plus 1 and it has eigenvalue minus 1 and vice versa. And that's the case when it won't be non-degenerate. So it's always short, but it's non-degenerate if this condition is satisfied. Okay, here is another example. So let's consider Lie algebra SL2 and consider enveloping algebra. And then mod out by the ideal generated by a central character. So we have this Casimir operator C, EF plus FE plus H square over 2. And it acts in the representation of highest weight lambda by lambda times lambda plus 2 over 2. And we will mod out by this relation that C equals to that. So, so then A is the algebra of regular functions on this quadratic cone X in C3, which is polynomials of X, Y, Z modulo X, Y equal to Z squared. So this is the nilpotent cone. And now I will put all the variables in degree 2. So my Poisson bracket is just the Kirillov constant bracket on the coadjoint representation of G. So it has degree minus 1. And to make it minus 2, I multiply all the degrees by 2. And then it's good to look at it from the point of view of representation theory. So you can decompose A as a representation of SL2 as in a direct sum of irreducibles. So this will have in each degree, you will have one irreducible of the corresponding highest weight. So direct sum of V sub 2m. This is a multiplicity 1 decomposition. So every summand occurs with multiplicity 1. And for this reason, there is a unique SL2 invariant quantization map. So there is still infinite dimensional space of quantization maps, but there is only one map which is invariant with respect to SL2. And that's because of this multiplicity 1 property. And then there is a lemma which says that the star product defined by this invariant map is short and non-degenerate if and only if lambda doesn't belong to Z, except that it's allowed to be minus 1. Because values lambda, well, lambda and minus lambda minus 2 define the same thing, of course, but positive integers have the property that this ideal is not maximal. So there is a maximal ideal, which is the annihilator of the finite dimensional reducible representation. And it turns out that this form that I defined has a big kernel. It's actually finite rank, and it descends to a non-degenerate form on the matrix algebra, which is quotient by this maximal ideal. But otherwise, it's non-degenerate.
Sorry, just a question. So you say this product, is it some kind of Shapovalov form, or what is it?
Well, it's I mean, you can compute it. It's computed in you know, old papers, and it has to do with you will get all kinds of 6J symbols and so on. but it's not particularly simple. I mean, it's even in this case.
Okay.
And the shortness follows, but the proof of shortness is very simple because it follows from the Clebsch-Gordon rule. If you tensor, as I said, in each degree we have an irreducible representation. Now, if you tensor two such representations, Vi and Vj, you do not go below absolute value of I minus j. This is what the Clebsch-Gordon rule tells you. And that's why you can never get, if you have an invariant star product, which it will be because it comes from invariant quantization map, it can never produce elements of degree less than absolute value of I minus j. So it has to be short by representations here. Any questions?
Sorry, question about the Moyal product.
Yes.
When we have the different, when we have the symmetric form.
Yes.
Yes. Is there? So obviously they arise from a different quantization map.
Yeah.
Is there an explicit formulation for that map?
Yeah, I think so. You can compute this map, but I didn't. I mean, both the map and the star product. I mean, you can compute it. It will still be invariant with respect to the maximal torus of SL2, and so you can compute it. It's not particularly pleasant, but it can be done.
Okay, thank you.
You get some kind of hypergeometric expressions. Okay, so now here is a generalization of this previous example, which is more complicated. So it works for an arbitrary simple Lie algebra G. And in this case, I will take X in G star, which is going to be the minimal nilpotent orbit. So it is well known that there are finitely many nilpotent orbits in G star, and the smallest one is 0. But then there is the next smallest one in terms of dimension, which is unique, and it's called the minimal orbit. For example, for Lie algebra SLN, this is the orbit of matrices of nilpotent matrices of rank 1. So they have the form F tensor V, where V is a vector, F is a covector, and F of V equals 0. And well, when F and V are not both 0. When are both non-zero. And so again, I put everything in degree 2, or the generators in degree 2. And then there is a quantization of this thing, which is, it's also well known. It's the quotient of enveloping algebra of G by the so-called Joseph ideal. So it's not, so this is a certain ideal defined by some quadratic relations. And it depends on one parameter when the Lie algebra is, oh, there is a misprint here. It should be equal to SLN rather than not equal. It depends on one parameter if G equals to SLN and has no parameters otherwise. For example, for SL2, this is just the ideal generated by the central character, which we discussed in the previous example. And then we have a decomposition. So the nice thing about this algebra is that we have it decomposes in irreducible representations in a very simple way. Again, there is a multiplicity-free decomposition, and in each degree, there is a corresponding multiple of the maximal root. So in degree 2, you are going to have V theta, which is just the adjoint representation, and in degree 4, you are going to have V2 theta, and so on. And there is a lemma, again, which is that there is a unique G-invariant quantization map, and it defines a short star product. And this star product is a non-degenerate for where you have to say that parameter is not integer for SLN. And it follows, well, in this case, we don't have a Clebsch-Gordon rule. When you take tensor product of such two modules, Vi theta and Vj theta, you get a sum of many things, not only of this form, but Vm theta can only occur in this sum, in this product, if m is at least absolute value of I minus j. So this weak Clebsch-Gordon is enough to conclude that our star product is short. So any questions about this? So these things are all well known, and they were in particular written in this physics paper by Beem-Peelaers-Rastelli. But the question is, in what generality do we have these short star products, and how to compute all of them? Because they were, in the physics, they arose as, multiplication in some operator algebra arising from quantum field theory. And they were interested in studying properties of this multiplication and noticed that it had this shortness property. And so, well, it turns out, it turns out that the generality in which this works is the so-called Hyperkähler cones. This is the subject of this conjecture that was made in this physics paper, and it was proved in our paper under some assumptions. So let me say, what is Hyperkähler cone? So Hyperkähler cone, actually, it's not easy to define this notion, and there is no good, not much good mathematical literature about it. But I'll give you some idea. So from algebraic point of view, it's just a normal conical Poisson variety. So just an affine cone, which is normal and has a Poisson bracket. And let's say it has of degree it's of degree -2. And then there is a differential geometric structure, which is a Hyperkähler structure on the smooth part. And this really means that you have a quaternionic structure on the tangent spaces. And some integrability condition. And it should be compatible in the sense that when you go to the singular part, it should not blow up in some sense. So in particular, you get a structure of a metric space.
Just a question. So this Poisson structure, how is it related to various symplectic structures of the Hyperkähler?
Yeah. It corresponds to the complex structure I. So there is I, J, and K, which are the basis of imaginary quaternions. Mm-hmm. For each of them, there is a complex structure, and for each of them, there is a holomorphic symplectic. So there is so there are symplectic forms omega I, omega J, and omega K, and there is a holomorphic symplectic form which is omega J plus I times omega K, which is holomorphic with respect to symplectic structure I. And that's the symplectic form for this Poisson structure.
So this is a complex Poisson structure.
It's a complex, yeah, it's an algebraic Poisson variety, a complex Poisson structure, and a Hyperkähler structure, which is compatible in this way that I just explained answering your questions. But also, you need to say something about singularity. So it's actually not so simple. And it's actually better if I, instead of talking about this definition, I give some examples of them, which are already interesting and for which the results of my talk apply. So here are some examples. So first of all, quotient singularities. So if you have a symplectic vector space and a finite subgroup, and you take the quotient, that's a Hyperkähler cone. And that's clear because you just have a constant quaternionic structure on this symplectic vector space. I mean, if you choose a compatible complex structure, so compatible, so it has a symplectic form. If you choose a compatible unitary structure, you get a quaternionic structure, and that's preserved by this group if your unitary structure is preserved. And the quotient is going to be this quaternionic Hyperkähler manifold, singular Hyperkähler manifold, Hyperkähler cone. So that's a very simple example, but still interesting. And then it turns out that nilpotent orbit closures for simple Lie algebras also have Hyperkähler structure, and they are Slodovy slices. This was done in the work of Kronheimer in the 80s. And then a big class is Higgs branches of three-dimensional superconformal field theory. So what are these things? So you have, so in this case, you still have a symplectic vector space, and you have some algebraic group G acting on the space, in fact, a reductive group, and you take a symplectic reduction, the Marsden-Weinstein reduction. And so this is a certain variety, and so this is also one of these. And in particular, this contains the class of Nakajima-Quiver varieties. And finally, conjecture also Coulomb branches for those three-dimensional theories. Those I cannot easily define right now. The mathematical definition is quite non-trivial, and it is worked out by Braverman, Finkelberg, and Nakajima, but it's too long to present in this talk. But this is also presumably a class of such cones in the case when they are actually conical, because they are not always conical. So any questions about this?
I don't think that they do metrics. I don't think they construct metrics.
Well, in the case of Hamiltonian reduction, so this is a Hyperkähler reduction. There is a procedure of Hyperkähler reduction which allows you to construct the metric.
No, in the Coulomb branches case, you mentioned the last one.
Yeah, that's right. But they don't construct the metrics. That's right. In fact, it's not mathematically, it's not known that they have metrics. Other questions? Okay, then what are these things from mathematical point of view? So from the point of view of algebraic geometry. So from the point of view of algebraic geometry, it turns out that a good approximation to the notion of Hyperkähler cone is a notion of a conical symplectic singularity, which is a purely algebraic notion. And so what is a conical symplectic singularity? This was defined by Beauville. And this is a normal affine conical variety, X, or scheme actually even, with a generically, yeah, well, let's say normal affine conical variety, with a generically symplectic Poisson bracket of negative degree, homogeneous, such that the symplectic form lifts to a regular 2 form on the resolution of singularities. So that's the last condition is the most important. It lifts to a regular 2 form, but not necessarily a non-degenerate one. So it doesn't define a symplectic structure on the resolution. Sometimes it does define symplectic structure and resolution. In that case, we say a symplectic resolution. And that's a subclass, which is especially nice. But even if not, and just extends to a holomorphic form, this is a nice class, which is called conical symplectic singularity. And I should mention that if it happens for one resolution, then one can show that it happens for all resolutions. And it is believed that under some mild assumption, these Hyperkähler cones should all be conical symplectic singularities. And this is known in many examples, in particular for quotient singularities, for orbit closures, orbit slices, for Higgs branches in many cases, and in particular for Nakajima varieties. And so from the point of view of algebraic geometry, we can think of Hyperkähler cones as conical symplectic singularities. But actually it doesn't capture all the structure. So Hyperkähler cones also has a non-holomorphic SU2 symmetry, which acts, so any Hyperkähler manifold has a complex projective line, a Riemann sphere of complex structures, which correspond to the unit imaginary quaternions. And SU2, but in general, there is no SU2 action that acts on them by rotation. I mean, in general, there is no action on your manifold, which corresponds to the section on the sphere. But for Hyperkähler cone, there is such an action. So all complex structures are equivalent in that case. And but this symmetry is not holomorphic because it moves around complex structures. Only the torus acts holomorphically on the complex structure, which is a fixed point for that rotation of the sphere. And so therefore, it's not easily seen symmetry in the setting of algebraic geometry. And somehow the main point of this talk is it turns out that these short star products are the algebraic incarnation of this symmetry. So it's a way to see this symmetry in algebraic geometry. And in fact, so in other words, I showed you this example with SL2, and there the shortness came from Clebsch-Gordon rule. And in fact, it always comes from that. but for this SU2 group, which acts non-holomorphically. So that's kind of somehow informally the main idea. And that's how it came up in the physics paper that I mentioned. So, so this gave rise to the following conjecture in that paper by Beem-Peelaers-Rastelli. So suppose you have A, which is functions on this X, which is a Hyperkähler cone. So this is a graded Poisson algebra as before. Then first of all, it admits non-degenerate short star products. And second, these star products are parameterized by finitely many parameters. So that's the main conjecture. And our main result is the following theorem. First, part one of the conjecture, which is existence of such star product, holds in many cases. And this includes nilpotent cone and more generally Richardson orbits of Lie algebras, also quotient singularities and Higgs branches with finitely many fixed points of Hamiltonian torus action. And this is still work in progress, presumably many other examples, and hopefully at some point we will be able to deal with all the relevant examples. And the second part is that part two also holds. So in the case of conical symplectic singularities, you can prove rigorously that there are only finitely many parameters in some sense, which will become clear later. So any questions about this?
I don't know whether it's a good time to ask that question, but why finitely many fixed points? Why this is a good criteria? I mean, how do you use it?
Actually, it turns out that more or less these parameters it turns out that the parameters correspond to those fixed points in some sense. It will become a little bit more clear later if I get to that point. Okay, other questions? Okay, so let me explain how to prove part two of this conjecture. And for this purpose, we use an approach suggested by Quantization. So basically, I was very confused. And before I talked to Quantization at some conference, and there was a 10-minute break between talks. And I spent 9 minutes telling him about the problem. And then he spent 1 minute explaining to me how to solve it. And then this gave rise to this whole paper, actually. So what he explained is the following. So the short star product is a kind of esoteric notion, which is kind of hard to relate to things that we know. But it turns out that you can relate it to the notion of twisted traces, which is much more familiar because it's related to Hochschild homology. So suppose you have a filtration preserving invertible linear map on your algebra. It's not required to be anything other than linear map and invertible. And then definition, we say that a linear function on our algebra is a G-twisted trace if it satisfies the trace condition with twisting by this map G. Moreover, we say that this trace is non-degenerate if the bilinear form it defines, trace of A times B, is non-degenerate actually in a strong sense, which means not only it is non-degenerate on the whole space A, which means left and right kernel are zero, but it's actually non-degenerate on each filtration piece, Fi of A. This is a stronger condition because, for example, it means the T of 1 is not zero. And the lemma, which sounds surprising, but actually is true and easy, is that if T is non-degenerate, then this G has to be an algebra automorphism.
Excuse me, Pasha, sorry to interrupt. So I don't understand this definition of G-twisted trace. For me, trace is an operator which acts nicely under changes of cyclic ordering. Whilst, so in this definition, it seems to me that for you, the ordering is quite important, or is it?
That's right, it's a twisted trace. If it was if G was equal to the identity, this would be an ordinary trace, which satisfies T of
Oh, yes, of course. Sorry for this. That was silly. Sure.
Yeah. Okay, and so so it's an algebra automorphism. It's a bit surprising because non-degeneracy seems to be just a generic condition. It should be true for a random trace that we take. How can it force some strong condition like algebra automorphism? Well, it turns out that the condition that G is filtration preserving is crucial, because if you have any non-degenerate linear functional like that, then on every degree you get some operator G which will satisfy this condition, just because if you have already a non-degenerate form on your finite dimensional space, then any other form is related to it by an operator. However, those are not going to be consistent between different degrees in general. So consistency of them between different degrees and the fact that they unite in a single map from A to A is really a very strong condition which forces the G to be an algebra automorphism. And now it turns out that if you have a non-degenerate trace, then and it is invariant with respect to the Z-mod 2 action, then you can construct a short non-degenerate star product. Namely, you have this bilinear form, which is the trace of the product, and because it's non-degenerate, you can construct a canonical orthogonal complement to Fi minus 1 instead of Fi. And this will actually be a complement because of non-degeneracy. And also it doesn't depend on whether you take it on the left or on the right, because G preserves filtrations. And left and right are related by G. And this thing, because it's a complement of I minus 1 inside Fi, it simply projects to this piece of the commutative algebra AI isomorphically. So we have these isomorphisms. And the quantization map can then be defined just to be the inverse of that map. And that is invariant with respect to S. And it defines, therefore, a star product on A, because we know that an invariant quantization map gives you an invariant star product. And this star product does not depend on the normalization of T. So we always normalize it to be T of 1 equal 1. And this is possible because it's non-degenerate, because T of 1 is not 0. And then the proposition, main proposition, is that this star product is short and non-degenerate. That's the first statement. And the second statement is that any non-degenerate short star product is obtained in this way, from a unique non-degenerate trace up to scaling. And in other words, this means that there is a bijection between short non-degenerate star products and filtered quantizations of A equipped with filtration preserving automorphism commuting with S, and the non-degenerate invariant G-twisted trace up to scaling. And the proof is quite easy. In fact, well, I don't give the whole proof, but basically to prove this, you need to construct the map back, because we constructed one way from trace to star product, but you need to construct the map from star product to trace. And simply you say that if A is equipped with a non-degenerate short star product, then we can simply say that bold A is just our commutative A with the new multiplication as before. And the trace in this case will simply be the constant term, or the degree 0 term. And then one can prove easily that T is a non-degenerate G-twisted trace for some uniquely determined map G, because I told you that if you have two non-degenerate forms, they're uniquely related by an operator, so this G is uniquely determined. So any questions up to this point?
So what's the formula for G? Do you have, or does it exist a good formula for G?
Well, I mean, it's basically on every Fi, you have two bilinear forms. One is T of AB and the other T of BA. So you take matrices of those forms and you multiply one by the inverse of the other.
So it's a kind of horror story.
Well, yeah, but it's not, you don't need to compute it. It's actually G is, because it's an algebra automorphism, there are very few choices for it. And so it's easy to compute in other ways. So this problem is not really a problem.
Okay, why is it important for, okay, in what you, okay, in the proof, why is it important that the star product is short?
Because you need to,
Just maybe to better formulate the question, if I did the same with a non-short star product, what would go wrong?
You won't get this condition that T of AB equals to T of B times G of A. So that uses the fact that the pieces, this form that you have, the pieces of this algebra A are orthogonal. So there is I mean, it's a short calculation, but in order for it to work out, you need this shortness condition of star product.
Mm-hmm. Okay.
Okay, so now I can explain how this part 2 is proved by describing the parameters for non-degenerate twisted traces, which also classifies parameters for non-degenerate short star product. And these traces are much more familiar objects, which is why this method is good. And so I will describe it in the case when we have a conical symplectic singularity. So if you have a conical symplectic singularity, well, sometimes there is the symplectic resolution, which I mentioned, but what exists in general is so-called Q-terminalization of X, which is a certain partial resolution of singularities. Basically, it means that you more or less resolve codimension 2 singularities, but it's more complicated than that, actually. So it's a singular variety in general. But it has you can consider it second cohomology. Let's call it H. This is because if X is a nilpotent cone of Lie algebra, in this case, we do have a symplectic resolution, which is cotangent bundle of the flag varieties. And in this case, H is just the Cartan subalgebra of our Lie algebra. And it has an action of a reflection group W, which is called the Namikawa-Weil group. And in the case of nilpotent cone, it's the ordinary Weil. And it's always a reflection group. So the quotient H over W is always a smooth object. And the theorem of Namikawa so Namikawa classified these Poisson deformations, Lossev classified quantum deformations, and they proved that filtered quantizations A lambda are parameterized by lambda lying in the quotient space H over W. So that's a finite dimensional space. And it remains to classify for a given lambda non-degenerate twisted traces for each of those algebras A lambda. And recall that any such trace defines a filtration preserving automorphism of our algebra, commuting with S. And because this algebra, its associated graded actually is finitely generated, its functions on some algebraic variety, any automorphism is determined by its action on finitely many degrees. And therefore, the group of automorphisms is an algebraic group. In fact, if X is a Hyperkähler cone in which 0 is a symplectic leaf, so you don't have translational symmetries, then actually it's a reductive group, because it turns out that its real form, the real points of this group, which preserve the Hyperkähler structure, is a compact group. And so for any lambda and G, there are finitely many finite dimensional space of lambdas, and for each lambda there is a finite dimensional space of G's, and we need to describe the parameters for the trace. And that's done as follows. So this trace is, by definition, it's an element of the zeroth Hochschild homology of a lambda with coefficients in this bimodule A lambda times G, where this is just as a vector space A lambda, and left action is just usual multiplication, and right action is multiplication twisted by G. So this Hochschild homology of algebra in a bimodule M is just a quotient of M by commutator of A with M. And then we have to take invariance under S, because our trace should be S invariant, and take the dual space. because the dual space is exactly those functionals here which vanish on this commutator, which is exactly this condition of twisted trace. And so it remains to show that this homology space is finite dimensional. Any questions up to this point? Okay, so I'm going to do it in the case when G equals to 1, and the general proof is similar, using the fact that we have a reductive group. I'll show, in fact, that the whole space of homology is finite dimensional without the condition that it is S invariant. And for this purpose, it's enough to consider its associated graded, but the graded is a quotient of the zeros Poisson homology, HP0 of AA, which is the quotient of A by the Poisson bracket of A with itself, where A is our Poisson algebra. So it suffices to show that this HP0 is finite dimensional. And this follows from the next two theorems, which were known by the time this paper was being written. One theorem is due to Kaledin, it's pretty deep. And it says that a conical symplectic singularity has finitely many symplectic leaves, algebraic symplectic leaves. So it has algebraic symplectic leaves. And then the second theorem is maybe not as deep, which we proved with Schedler, but still it uses the theory of D modules. So it's a pretty interesting theorem. And it says that if X has finitely many symplectic leaves, then this space is finite dimensional. And so that shows that the moduli space of these short star products has kind of three kinds of parameters. So first parameter is lambda, which is parameter of quantization. And then for every lambda, we have to consider this group G, which is actually the same for all lambdas. And then for any element of this group, we have to, and for any lambda and for every G, we have a finite dimensional space of traces. And of course, we have to select only those that are non-degenerate, which is going to be some open set there. So any questions about this?
Can I ask
yeah.
a question about the effect of G on the quantization? Like if you set everything else to 0, would G kind of give you like a Vandenberg non-commutative algebra type of thing? Like this Vandenberg twisted?
No. It's no. G is responsible for this bimodule, not for the algebra. I mean, the algebra depends only on lambda. But we take homology with coefficients in this bimodule, A lambda times G. And so that's how G contributes.
Mm-hmm.
Okay, and so finally, I want to, can I have another 5 minutes?
Yeah, sure.
Yes.
Pavel? Sorry, I have a question, Pavel. Is this the only place you use the hyperkählerness in order to conclude that this automorphism group is reductive? Is that where the hyperkähler
I
is
think
used?
it is the only place. Yes.
But perhaps I would suggest let Pavel finish the next 5 minutes, and then we can have all the questions we want. Would it be okay?
Yeah. All right. So so let me talk about existence of these twisted traces. So there are, so we have to show that this space, cohomology space, is not 0, first of all, and also we have to show that it contains non-degenerate elements, and then the generic element will be non-degenerate. And in fact, we show in the examples that we can handle that non-degenerate twisted traces exist for generic quantization parameters. And so, and there are at least 3 approaches to this, which work in different examples. So the first most interesting approach is explicit construction of traces. And this can be done by using representation theory. So suppose we have a category O in our setting. So there is a category O of representations of this A lambda. So for that, you need some kind of grading, which is usually defined using a one-dimensional torus inside the group of automorphisms, which will tell you which part of the algebra is positive and which is negative. And this happens, for example, in the following cases. So first of all, you can consider these quotient singularities. But when V is a direct sum of Y plus Y dual, and the group preserves this decomposition. So, and in this case, this A lambda is what is called spherical Cherednik, rational Cherednik algebra. Another example is nilpotent cone. This is the classical story with category O of Bernstein, Gelfand, Gelfand. And then you have a simple Lie algebra, and A lambda is quotient by the central character. In this case, we have the usual category O. And the third example is if you have a Higgs branch and the maximal torus of G of this group G acts on X with finitely many fixed points, then it turns out that there is category O and its highest weights are parameterized by those fixed points. So it turns out that filtration preserving derivations of A lambda are inner, and therefore for M and O we can define G-twisted trace in the following way. Trace of A is the trace in M of A times G, where A is in your algebra. Well, there are some issues with this definition. One issue is that M is infinite dimensional in general, so what do we mean by trace? And the second issue is that G is not an element of our algebra, it is element of the group of automorphism. So generically, G is exponential of some element of the Lie algebra of this group. And because the derivations are inner, this Lie algebra actually sits inside this A lambda as the degree 2 part. And so this exponential is some infinite series. So there are some issues with defining this trace, but you can define it as an infinite series, and then you can derive some differential equations for it. And this will imply that this series converges to a multi-valued analytic function on G, a priori multi-valued. Actually, it can be shown that it's a rational function, but that's more subtle. And then this gives you a trace, and then you can sometimes show that it's non-degenerate. Then another type of thing is deformation arguments, which simply says that if you take, let's say, example is the same as before, except gamma does not require to preserve decomposition. So in this case, you get symplectic reflection algebras, spherical symplectic reflection algebras, which we defined with Ginzburg 20 years ago. And in this case, there is one point, lambda equals 0, where this algebra A lambda is the Weil algebra, invariance in the Weil algebra. And then you simply can take the Mayal-Weil product, which is short and non-degenerate, and restrict it to invariance. So it's going to be fine. And this is for lambda equals 0. But then by deformation argument, you can show, since these traces exist for lambda equals 0 and easy to construct, they will also exist for generic lambda, because the dimensions of all spaces are independent of lambda. So this is another kind of approach. And the last approach is positivity. So for nilpotent cone of Lie algebra and G equals to 1, this space is one-dimensional. And so there is only one trace up to scaling. And it's very easy to construct this trace. You just take for every lambda. So if lambda is a positive integral weight, dominant integral weight, you can compute, there is a finite dimensional reducible representation, and you can compute the trace of A in that representation. And then it turns out that this depends polynomially in lambda. So you can interpolate it. And of course, for lambda integer and positive, this is degenerate, has finite rank. But if you restrict it to particular Fi and you take a generic value of lambda, then it turns out that it is non-degenerate. And the way to see it is very simple. You look at this form, and then you take B equals to A dagger, the Hermitian adjoint of A. And then this inner product of A with A dagger is going to be positive in low degrees, because this is a unitary representation. And therefore, for generic lambda, it's non-degenerate. And that means that it's generically non-degenerate for all Fi's. Okay, thank you.
Well, thanks a lot. So, any questions or comments? Maybe it's a good idea to use this raising hand system. So
Yeah,
that,
so I see some hands. So what do I do? Do I need to do anything?
at the moment, I don't see. Let me see.
Those
I
I
see
think were
Anya raising hands, for example.
Yeah, strange. They don't come up at the top of the list for
No,
some.
I was clapping. That's
Yeah,
a
it's just
different
clapping.
It's
No,
clapping. Okay.
Yeah, two. Here it is.
Okay, Marta.
That I was clapping also.
Okay, okay.
Ah.
So any questions? Any hands raised? If not, I have, maybe let me start. I have a question. So you were solving this this question about the finite number of parameters, and I understand it was a conjecture by the physicists, and you found many very interesting things. But why that question of finite number of parameters? Why was it a good question? That I haven't quite.
Well, why the physicists needed
Yeah,
it?
for instance.
Well,
yeah.
actually, I think they still, since then, they had a different approach where this was less necessary. But when the original paper was written, they wanted to calculate. The point is that they had this they had some operators, and the way these operators multiplied was according to a star product, which they showed has to be short because of this SU2 symmetry. And then they were hoping, this is such a strong restriction that they can actually calculate the star product up to finitely many parameters. And then they were hoping to compute those parameters as well by using positivity properties. And actually for A2 singularities, they did succeed in that.
Okay, but in general, your classification, it looks at the moment very complicated, right? There are 3 types of parameters, and maybe each of them contains thousands of them, right? It's possible.
No, yeah, that's true, but it's not that. Actually, we understand very well those spaces of parameters. We understand in all examples. We understand this H2 space, and then we understand the automorphism group very well. And then this homology is when you have a symplectic resolution of singularities, this homology is the top cohomology of the resolution. So we understand it pretty well also. Mm-hmm. And so this gives you actually a way of computing, especially if you have category O, then you can actually compute these traces as traces and representations. And so this gives you a pretty effective way of computing things.
Okay. More questions?
Yes, I have a question.
Sorry, Nicola?
Yes.
No.
Yes.
Yeah, okay. Yeah, but you know, if you use this raising hand system,
yes.
Nicola?
Okay. So just maybe that was connected to what you were saying, but in the case when G is not the identity, the automorphism, your proof of the finite number of parameters relies on the results on Poisson homology with coefficients. Like, I mean, you have some results of this kind, because you said when G is the identity, then you show that you have this zeroth Poisson homology that's finite dimension.
Well, yeah, in a sense, but actually it's what you do. For example, when G has finite order, then you can take the fixed points of G, replace this variety X with the fixed points of G. And it turns out that this theorems, that is also going to be a symplectic singularity. And actually those 2 theorems that I quoted for that variety will imply the finite dimensionality of this space. Okay. And if G is then the next case you do is when G is a semi-simple element, and then so it lies in some torus, and then you can take generic element of that torus, which is a finite order, and apply this kind of argument. And then if it is not semi-simple, then you factor it as a semi-simple and unipotent element. and you can use, there is some, you have to do some work, but using the fact that the group is reductive, you can show that actually for any element it's true. In general, symplectic singularity doesn't have to have reductive group of symmetries, and if the element G lies in the nilpotent radical of this group, then I do not know how to show that it's finite dimensional, this space.
Okay, thanks. Okay, Tamas?
Yes, I'm interested in this SU2 action you mentioned. So does it act the group on the spaces with Hyperkähler isometries?
Yes, yes, yes.
Isometries of the metric, sorry.
Yeah, yes, yes.
And then do you have a twistor space?
Yes, I think so.
And then on the twistor space, do you have a holomorphic action maybe of the?
Yeah, yes, I think so. Yeah, but
So maybe something quantization could be happening on the twistor space.
yes, I don't know that stuff very well, but there is actually a paper by Hitchin and collaborators which discusses somehow this story, I think. So, yeah, unfortunately, the theory of these Hyperkähler cones, the differential geometry has not been worked out in great detail. So it's really hard to prove anything about general Hyperkähler cones.
Okay. So, but where is the definition? The physicists have it, or?
There is a paper of Swan, but it's not. It's not quite what one needs. So I think the honest answer is there is no satisfactory definition. My definition, but I don't know how to actually do anything with it, is that there should be a Hyperkähler structure on the open part compatible with holomorphic symplectic structure, and it should define metrics. So it should extend as a metric space structure continuously to the whole thing. So that should be sufficient, I think, but I don't know how to actually, there is some analysis one has to do, so I don't know how to actually develop a fully rigorous theory here.
Okay, more questions? I got a very naive question. Probably I should have understood it from the talk. In the case of the Moyal product, what is G? Is G equal to 1 or?
No. The G can be in that case you can look at the so first of all in that case you can have the group is not reductive because you can have translation symmetries, but that's not important. You can take the reductive part, which acts the preserving degrees, so to speak. So then the group is SL2, and so G will lie in this SL2 group. So so actually you can take any element of this SL2, but of course it only matters up to conjugation. So really, for example, if you take a semi-simple element, it will be in the maximal torus.
No, wait. Now I'm really getting lost. Sorry, because I think you said that those short products are in one-to-one correspondence. I forgot with what traces.
Yes. So remember, I had this B. So remember, you had this element B that this matrix B, element of symplectic Lie algebra.
Oh, okay.
And so it turns out that the element G, it will be in the symplectic group, is the Cayley transform of this element, which is B plus 1 divided by B minus 1. Oh. Remember that both of those have to be invertible.
Oh, okay. Okay, sounds very interesting.
So there is a birational isomorphism between symplectic Lie algebra and symplectic group, and also orthogonal, which is B goes to B plus 1 over B minus 1. And that's exactly what it is.
Okay, so any more questions or comments? Well, if not, let's thank Pavel again. Thanks a lot.